Hello and Assalamualaikum everyone. We are from Group O and our group members is Farhan Faqrullah, DURAR CAMALIA, NURUL IMAN, Muhammad Faiz and Ian, COLIN JUSTRIN.
Assalamualaikum warahmatullahi wabarakatuh and good afternoon. My name is NURUL IMAN and today my group will be presenting a critique on a journal article that explores the role of microscale chemical interaction in catalyst design. The article we reviewed is titled The Multi-Scale Phenomena in Heterogeneous Catalytic Processes, the Impact of Chemical Phenomena under the Microscale Level on the Catalyst Development and Design, which is written by Chant, Zhu and Lin, and it is published in 2004 in Chemical Engineering Science. It explores how extremely small particle scale chemical interactions, particularly at the nano and the sub-nano levels, can significantly affect the catalyst performance and also the structural ability. The authors focus on two catalyst systems, which is the platinum tin on alumina, which is used in the hydrocarbon dehydrogenation, and also the molybdenum on HZSM5 used in methane aromatization. What makes this article stand out is how it connects the microscopic detail like surface structure and the active site behavior with large-scale outcomes such as selectivity and resistance to carbon disposition. The authors also used advanced techniques like ZAFS, which stand for X-ray absorption fine structure, FTIR, which means Fourier transform infrared spectroscopy, and also the Masser-Bauer spectroscopy to study this system in depth. Overall, the article emphasizes how understanding surface-level chemistry is essential for designing more efficient and stable catalysts in industrial processes.
Moving on to the first critique point, for my part, the title is Strength and Limitation of Research Methodology. The study by Tian Su and Lin 2004 stands out for its strong use of advanced characterization techniques, including XAFS and MOS spectroscopy and FTIR. These tools allowed for detailed analysis of catalyst structures and help establish valuable insights into structure and performance relationships. The research focused specifically on two model systems, which are platinum stannum on alumina and molybdenum on HZSM5, providing a deep investigation into how sub-nanometer features influence catalytic activity. However, the methodology do have limitations. The catalysts tested were only those developed in the author's own lab without comparison to other supports or variations in metal loading. This narrow scope limits the broader applicability of the findings. While the authors do touch on the catalyst deactivation, they do not address the regeneration part or long-term stability, which are very crucial for real-world use. In short, the study is technically strong and insightful, but will benefit from broader validation and practical during durability testing. That's all.
Right, next we're going to take a look on the critique point number 2, which is titled Weak Link Between Concept and Application. So the first weak link is advocate multi-scale design in theory. The article proposed a theoretically appealing framework that aimed to link macro-scale surface phenomena with a macro-scale reactor performance such as yield, efficiency in a chemical reactor. This means the author are advocating for a multi-scale design approach with a different scale of catalyst behavior are considered in a unified model. However, this advocacy remains largely conceptual rather than practical. Number 2 is a lack predictive model or design tool. The author do not provide predictive model tool or concrete design methodologies that could help engineer or researcher quantify or stimulate the micro to macro relationship. Number 3 is no suggested experimental workflow or simulation. Although the article emphasized the importance of detailed surface analysis, it failed to include any proposed experimental method or simulation workflow that would allow the researcher to implement or validate the conceptual framework. This omission makes the researcher inaccessible or experimentalist or those looking to integrate the concept in the real-world testing or development pipeline. Number 4 is the misstep for scaling up to industrial level. The article does not consider a scale-up factor such as economic viability, regulatory standard, or pilot scale testing. This is a major shortcoming as a practical catalyst design for industry must be proven at increasingly larger scale and under real condition. And then lastly is more conceptual than actionable for engineer. While the framework may have an academic value, it is described as not well developed in terms of implementation. Especially for engineer working in an applied setting, it lacks practical steps, tool, or integration with a modern standard, such as life cycle evaluation or sustainability measure. That's all.
Next, I will be sharing to you guys on how this study helped to improve catalyst design and what it means for our future. First, the study showed that very small interaction, smaller than nanometer, that are actually very important to how the catalyst work. It also explains the difference between two active sites that we call M1 and M2. Both are needed because they are do two different jobs. This is called by functionality, and it helps the catalyst to work better and last longer. Because of this, scientists now can design catalysts in a smarter way instead of just guessing what it works. This paper also suggests that in the future, this kind of knowledge can help to build a better computer design and for catalyst design. Lastly, the author said that we need more studies on the different materials so that we can create a general rules for designing catalysts that work in many cases and situations.
In our analysis, we leverage AI tools like ChatGPT, DeepSeek, and Gemini to streamline the research process. These tools help us summarize dense scientific content, structure our critique more clearly, and identify gaps such as opportunities for predictive modeling that strengthen our review. Beyond saving time on technical reading, AI also assisted in generating ideas supported by recent literature and brainstorming ways the article could integrate AI-based methods. However, it is important to emphasize that we used AI as a supportive tool, not a replacement for our own critical thinking and expertise. With this approach, we were able to enhance both the efficiency and depth of our work.
Last but not least, this article underscored the importance of micro and sub-nanoscale chemical interactions in determining catalyst performance, particularly in terms of the selectivity, stability, and also the resistance to deactivation. Through its focus on active site synergies such as the distinctions between M1 and M2 sites in platinum tin on alumina and the bifunctionality of molybdenum on HZSM5. This study highlights how structural nuances at the molecular level can directly influence macroscopic catalytic behavior. The effective use of the advanced characterization tools including the ZAFST and FTIR enables a detailed understanding of these interactions. However, while the theoretical foundation for a multi-scale approach is very well articulated, the study actually lacks the necessary predictive models and also the practical frameworks to translate this finding into a scalable design strategies. Moreover, the research is confined to a very limited set of catalyst systems developed within the author's institution, which also raises the concerns about the generalizability. Nevertheless, this article contributes meaningfully to the discourse on a rational catalyst design and also offers a mechanistic foundation that future studies could expand upon to develop more transferable and also application-driven methodologies. That is all from my group. Thank you.